life, there's a ton of microbials. So how are we going to control this? So you can use sterilization, so trying to actually remove or destroy all of the microbes, versus a disinfectant, which just reduces the number of pathogenic microbes. So getting to absolute zero of microbes is kind of hard sometimes, especially to do it so that it doesn't hurt us. And so if you can just reduce the number far enough that they're not going to cause a problem, then that's pretty much good enough at some points. Antiseptics, so it's a disinfectant that's non-toxic enough to use on the skin, versus sanitation, which is a disinfectant to reduce the pathogenic microbes to meet public health standards. Okay. So you can do pasteurization. So use, this is what's common in all food. Pasteurize things, you heat kill the microbes. So milk, fruit juices, wine, beer, they're commonly pasteurized to make sure there's no microbes in it. So I'm just talking to some of you about how important both that is.
What's she saying? Milk, juice, beer, fruit juice. Oh, fruit juice.
So suffixes with stasis, with static, will inhibit the growth of microbes, versus side or sidal, which will destroy or permanently inactivate a particular type of microbe. So inhibit.
Stasis inhibits
The growth of microbes.
Inhibit.
Side and sidal.
Okay. So it's one of those things where kind of start picking up on the vocab and start just making it easier, especially if you guys are going into healthcare, so you can start looking at some of the different things you're going to be working with. Is it going to inhibit growth, or is it going to actually kill the microbes?
Oh, it's right here.
Like fungicides, they'll kill fungus and hyphae and spores and yeast. So it's kind of like what you're actually looking at. Your book has 9.1 is a great little table. Okay, what the terms are, the definitions are, what are some examples of these, and then some random comments. It's like, okay, commonly we use iodine and alcohol. They're great at reducing the number of microbes or viruses, and they're safe enough that you can use them on humans. So these are the disinfectants whose strength has been reduced to make them safe for us to use. I mean, some of them you have to kind of tone them down slightly, but it was a great little chart on all of the different, has the static versus the sides, so telling you what they do. So, if we're going to have to figure out how to kill or treat some kind of microbial, we have to figure out where are we doing this. You can use harsher things on your skin than when you put it inside. You don't really want to kill everything inside of you. You have a nice thick skin layer that helps protect us. So, okay, are we treating something internally or externally? And what are we treating? Because different microorganisms are susceptible to different things or different amounts of some kind of whatever we're putting on them. And so we talked about endospores and how resistant those are. So if we're trying to get rid of endospores, then we need to do a whole different treatment than if we're just trying to kill some coli. We also have to think about some of the environmental conditions. So, you guys will be seeing today with your plates, what does temperature and what does pH do to these microbes? Also, if we're looking for something to control this, ideally the agent should be inexpensive, it should be fast-acting, have a stable shelf life, and capable of controlling the microbial growth without being harmful to us or to the animals we're using it on. So the effective temperature on the efficacy of antimicrobial control. What is efficacy?
How effective it
Yeah, 100, that's right. So, you can see just changing the temperature can change the number of living microbes. And so this is why when we want to sterilize things, we autoclave them. Because we raise that temperature up for a short period of time. But, I mean, if we're looking at, this is what 20 degrees does, you know, it takes a while for them to die off, 10 minutes, versus 45 when we get killing 4 minutes. Well, if we're doing 4 minutes at 121 degrees Celsius, you're going to be pretty sure a lot of it's dead. It's dead. Okay? So, changing the temperature, this is why we really wanted to know what is the optimal growth of these microbes. Because if we know it's optimal, then we know how to kill them. So a nice little chart kind of telling you relative susceptibilities. So which ones are, easy to kill versus more resistant ones. So if we're trying, so it's one of those things where depending on what we're going to be trying to kill or disinfect, how hard is it going to be? Endospores are up there. They're not going to go away very easily. Prions are just pieces of protein. They're already misfolded, so they don't really care if it's hot. But this is where kind of the gram-positive versus gram-negative plays a difference in how well that cell wall, that extra coating, plays a difference in how well it's going to be impervious to the antimicrobial agents. Yeah. Envelopes. So we're going to talk about viruses more when we get to, I think it's chapter 13. But basically, is it a naked virus or does it have an envelope or encode and stuff? So it's just, what's the packaging on the virus? That make sense? Okay. Yeah.
Why is the gram-positive bacteria more susceptible if it has a thicker cell wall?
Different kind of cell wall. Because, it's one of those things which, I don't know why it is, but just because of the way, that breakup, actually I do know, because most antimicrobials are targeted to stop that. So we'll get to that actually, because of how that linkage is. It's a very common, very basic linkage, and so there's been a lot of things that have figured out how to stop that. It's actually the most common way of stopping it. And so the negative, they don't have that, so it's not as easy to kill them because an easy way to kill a gram-positive is you stop them from being able to make their cell wall. It doesn't really work with gram-negative. Okay, so how do we control microbial growth? How do we damage it? There's only so many methods of stopping microbes. You can damage the cell wall. You can damage the membranes. You can damage the proteins. You can damage the nucleic acids. So, there's only so many points. If you can, you have to figure out how to inhibit something. Yes.
When you say damage to proteins, is that the same thing as attacking the ribosomes, which damages the ability to produce the proteins? Same thing, okay.
Well, yes, that is another method which is in that general category of you mess with the proteins. So you can damage a ribosome, which can either damage the protein or not make the protein. So it can do both, but ultimately you're stopping
Both
protein.
fit into the middle category.
Yeah, because you're messing with protein production. I mean, if you mess with protein production, you mess with DNA replication, or if you mess with translation, transcription, replication, or any essential function, like micro, the basic things. But if you think about it, there's only so many modes of action. Because if a cell figures out how to get around you trying to stop translation, then every other thing that does it the same way isn't going to work. So that's why we have a big problem with the antibiotics. Because once the microbe figures out a way to get around a certain antibiotic, everything in that family uses the same mode. And so they're now resistant to all of those. So you have to switch to a different mode of action. So alterations of cell walls. Cytoplasmic membrane, if you can stop or control the passage of chemicals into and out of the cell, you know, if you punch holes in that cell membrane and then the cell starts to leak out, really not a good thing for the cell. Also damaging proteins, if it goes in and it messes up that three-dimensional shape. That's another method of messing with proteins that makes it so that they're no longer functioning the way they're supposed to. The cell's not going to survive very well. This is why you can do that, you know, like you can damage proteins, you can damage the nucleic acids with heat or radiation or, you know, things like that, which can actually mess with them without, you know, so you can kill them without having to actually get inside of them. Okay. Measuring microbial control. So this is disc diffusion, the Kirby-Bauer method. So you spread bacteria on a plate, you get a nice pretty lawn or what would become a lawn, and you can then put these little filter discs with some kind of microbial control agent. So you can basically kind of see how well does this work. And so you guys are going to be playing with this, I think, tomorrow. So you get to actually just put one down and then see what is the zone of inhibition. What is that area where no bacterial growth is? You know, so these don't have a zone of inhibition, so these aren't working to kill that microbe. Whereas some of these you can see are working much better than, like, say, that one. Rate of microbial death, so decimal reduction of time, DRT or d-value. So what is the amount of time required for a 10-fold reduction in microorganisms at a given temperature? And so it's, you know, logarithmic scale of, you know, how long does it take before I go down? So 90% go away, 90% go away. So you get down to, so you have that 10-fold reduction.
About every 15 minutes?
Well, for this particular one, yes. This would be every 15 minutes. But you can set up DRT or the d-value per microorganism. If you want to know, well, if I have E. coli and I put it at this temperature, how long will it take to die? So, I mean, you guys in a way did this with your stuff yesterday. You put it in there 5 minutes, 10 minutes, 15 minutes, so you can see how far down did you get. So you didn't necessarily go all the way to where you could kill everything, maybe not, because you were, you know, you're at 70 degrees, so different temperatures. So you have to look and see how does that change things. It's all based on temperature and the microbe you're using. So what is the amount of time required for this 10-fold reduction? Okay. So this was something that was confusing in the book, because they talk about going from, you know, 90%, you go from 1 billion to 100 million. But if you think about it, it really is, it's, you know, you have 1 million, you drop down to, you have 900,000 deaths, that's 90%. It still means you're going to have 100,000 microbes alive. So you went from 10 to the 6th, 10 to the 5th. So it's one exponent. This is where you get that 10%, okay? That 10-fold reduction. And so it's the exact same thing, it's just trying to make it a little clearer, the fact that, you know, you're looking at kind of turning this line into a chart that makes it easier to see that you're getting rid of 90% every time. And so kind of like with half-lives, you don't get rid of everything just because you got rid of 90% that first minute. That doesn't mean that you're going to get rid of the other 10% the next minute. You're going to keep getting rid of 90% every increment. So that's why it takes 6 minutes to get down to one survivor. So it's just, that's the rate. You can't expect to kill everything. I see questions brewing.
Would this be per milliliter of fluid, or?
Yeah, so it's per your fluid volume or what you're doing. So I mean, that's what you're figuring out. That's the entire point of this, is your rate of microbial death, is your d-value is how quickly will it go down? Where's my 10-fold reduction? So this is just to kind of help
And is this due to an exposure to an increased temperature or an increased pH, or what is causing this temperature
Well-
increase, or could it be anything?
It's due to at a given temperature. So, I mean, you can set it, what is the death rate at a given temperature? You can increase the death rate by adding other things to it. You know, and you can have those little asterisks or whatever. Okay, well, if I also add bleach, what does it happen? And if I add, alcohol, what happens? But V value is just the amount of time required for a tenfold reduction in microorganisms at a given temperature.
So it's always expressed in minutes or time units?
Because you want to know how long it's going to take to kill these things. Okay, so the whole idea in this one takes 1 minute for the tenfold, 90% to die. Okay, so you get that decimal reduction number, so you have your organisms, you have the different values, so the D rate at this temperature, you know how many minutes it takes, so you get it based on time. Okay, so if we're looking at Clostridium botulinum, if we're at 121 degrees, it's going to take 0.2 minutes for this to drop 90%. Now, if you're at 101, it's going to take 20 minutes. And so it's a different death rate.
Drop to
Based.
90%, right?
To drop to 90%, yeah. So, I mean, basically it takes a lot longer to kill them if you're at 100 degrees versus 121 degrees. I mean, with pasteurization, this is the same thing. If you hold it at a temperature that's warmer, you'll eventually kill everything. But most companies, that takes too long. And so they make it really hot so that they can do a flash pasteurization. You know, there's some people who say that, oh, that ruins the flavors because you're killing a lot of things, you're denaturing proteins.
Nutrients.
But company-wise, it's cheaper because, I mean, come on, you get 90% gone in less than a minute versus 20 minutes to get 90% gone. Okay? Does this make sense? Does this help make more sense? So you can have different D rates based on temperature. Okay? So it all depends on what you know you're trying to kill. And versus what is it, salmonella? You just have to get up to 60 degrees. 90% will be dead in 0.4 of a minute. Okay. Questions? Heat-related methods. So you can do moist, you can do dry. Moist heats, they're used for disinfectants, sanitizing, sterilization, autoclaving. You actually use steam. So you have steam plus pressure because that makes it so things don't boil. It really sucks to have your media that you've carefully prepared boil over and all of a sudden you're not quite sure what the concentration of salt is anymore. So raise the pressure, it won't boil, but you'll still kill everything. Pasteurization, talked about, reducing the microbial populations by heat sensitive. So flash pasteurizing, so 72 degrees for 15 seconds, or you can do like ultra high, so 134 degrees for 1 second. And so you can see where companies would just be like, oh, well, this only takes a second, let's do that one. It's because in the long run it saves them time and money. You can also do ultra temperature sterilization. So versus just trying to kill everything, you can get that 140 degrees, 1 to 3 seconds. You know everything's dead at that point.
They're not actually doing that in 1 second though, right? It takes time for it to get up to 134 degrees and then it takes time to put that down again.
What I've seen that they do is they have these bar exchange systems, and so the milk is going up, so that you have them passing by each other. So the hot stuff is warming up the cold stuff and vice versa. And so that way by the time it gets to a certain point, it spends one full second at that temperature, and then it's going through the back part of the pipe and cooling down, giving its heat to the other part.
The process itself, so 1 second, that's what I was saying.
The whole process does not take 1 second, but it's held at this temperature for 1 second. So other methods using moist heat, one that we commonly do if you kind of don't want to do it at home would be boiling. You know, how many times have you decided you're going to make some kind of sauce or a marinade? You want, you know, the marinade you had on your steak, you want to use that as a sauce. Boil it for a minute, and you know that you've killed whatever microbes could have been in that raw steak juice. You know, yeah.
Just noticing, like, no, bacteria that do make fermentation.
Yeah.
It's like, does it kill those bacteria too?
Kills the bacteria that do fermentation.
You know, like when you're pasteurizing it.
It kills everything.
So it won't ferment.
No, like that's one of the things with like grapes and wine is that used to be that they would let the natural yeast ferment the grapes. Now what they do is they pasteurize it, kill off everything, and then add in their specific brand of yeast because they've worked for years and years and years to develop the yeast that does just what they want. So they add it back in. So yeah, it kills everything. Cheese, you flash do the milk, kill everything, add in the bacteria you want, give you the flavor you want, whatever type of cheese you're going to make out of that milk. One of the things with boiling is the time you boil is important because as we were talking about the different temperatures, since it's a lower temperature than what you can get up to when you use an autoclave, sometimes you have to do it longer. And also elevation matters because water boils at different temperatures at different elevations. And then you also have some things like endospores that can survive boiling. So if you're trying to get rid of those, you have to try and use some other kind of method. Dry heat. What are we using here? Flaming. We also use incineration. We don't use that because we kind of like our eyebrows. But you know, general flaming of flame loops is a way of sterilizing the entire loop. Baking, you know, you're doing a heat for lower heat in that case than flame for a longer period of time. That can sterilize and get rid of things. That's why our food is safe for us to eat. You have to get it to that certain temperature to make sure you've gotten rid of the microbes. You use the dry heat for things that cannot be sterilized using moist, or to help, you know, if you don't want to denature some of the protein sometimes or oxidize. And so a lot of times it requires higher temperatures for longer, which is why they like doing the moist heat, but it is a viable method. I mean, we really don't want to be autoclaving flame loops every time if you just stick them in a fire and wait for them to cool. Oh, that's fun. So, figure 9.7, sterility indicators. What I thought was kind of cool is the way they were figuring out methods of, does this kill everything? And so they would have rich media or nutrient media in here, in a little flexible, big flexible plastic vial, crushable glass ampule. It has a pH indicator, so this means, you know, we've been playing with these. You know that bacteria, when they start eating, they'll change the pH. And then they have an endospore strip. So they put endospores in there. And the entire point was to see how long does it take to kill those endospores. So you autoclave it. It's a nice flexible tube, so you're capable of just squeezing it. You break that little ampule, which means you now have rich media on that spore strip. And then you can see you have yellow media. That means the spores are viable and they were able to start growing. If you have red media, that means the spores were killed. And so everything's nice and sterile. And so it was a method of very clearly seeing what did it take to kill these endospores. And so, I mean, you can see how you could easily do this with just about anything you're trying to watch and see if it grows. So I thought it was a nice, very visual method of seeing what's happening. Other other physical methods, you can do refrigeration, lyophilization, freezing, desiccation, filtration. So these are other methods of sterilizing things. So now okay, you guys are going to be doing a whole bunch of experiments tomorrow. We don't have class on Thursday, so everything's going to be growing. So what we're going to do is we're going to pull them out, probably Friday morning, because I don't think anyone wants to be here Thursday, and we'll put them in the fridge. And so then everything will stop growing. It'll be way reduced metabolic rates, and so you kind of can slow everything down. It's why we refrigerate food, because whatever microbes are on there, if you have it out, they're at a nice warm temperature, they're going to grow. If they're cold, they're not going to grow very fast. That's also why if you leave them for too long, they eventually overtake the cold and still grow. So you can use refrigeration, you can use freezing. Most things have a really hard time living through the freezer. Some things can, but most have a hard time with that. Desiccation, drying them out. I mean, everything we've talked about is we're trying to protect these cells. These cells are trying to stay moist. So you purposefully dry them out, like when you was beef jerky, you're just drying those cells out. That's how you can store it, because you've killed everything. There's no moisture, nothing for them to live on. You're drying everything out. Filtration. We have filters that are pores that are so small microorganisms cannot pass through them. So this is a light microscope of what a filter would look like, and so you can see the little tiny pores. You see much bigger microorganisms in comparison. I mean, again, remember we're playing at 3 micrometers, so not even big. When we talk about refrigeration, we're talking about anywhere between 0 and 7 degrees Celsius. And a slow freeze is more effective than a quick freeze, just because you're really, it's one of those things they found over time. And if you do the lyophilization, you do this for a storage purpose because it prevents the formation of damaging ice crystals. The reason why freezing is so damaging is because water molecules freeze into nice little shards. So,
Doesn't the water also expand as it's freezing and cause damage that way?
they have cell walls, they don't notice that necessarily.
There wouldn't be there still wouldn't be any
There will be
damage to the cell
some.
wall as the water expands and freezes.
There'll be some, but it's more of the freezing and making the shards.
Yeah.
So it's, if it was just that they got a little bigger, I don't think the cells would notice, but they got bigger and sharper, so the cells kind of really notice that. I mean, that's one of the common methods for cracking open E. coli cells is you do freeze thaw. Liquid nitrogen, hot water, and just go back and forth, and the cells will all crack open. To break open yeast cells, we actually use little tiny glass beads in a bead beater and basically put them in a blender and whip it around and let those glass beads start shearing them. So these cells do not want to come open nicely. Osmotic pressure, another thing you can do to inhibit microbial growth. We've talked about this one. Salts and sugars in food. Why does that work? What are we doing? We're making what kind of environment for the microbes?
Hypertonic? Oh,
Isotonic.
ISO is the same.
Hypertonic.
They're not happy.
I just said
Okay.
If we're making them unhappy,
Oh, okay.
and they have a lot of stuff on the outside, it's what kind of solution?
Hypertonic.
Hypertonic solution, okay? So you can either, you can make this hypertonic solution of sugar, salt, so that they'll lose water. And we've talked about some of the extremophiles or whatever who they have learned to grow in these high salt environments. So some fungi have a greater ability to survive that, but messing with the osmotic pressure is a way to control microbial growth. It's why we cure things with salts or lots of sugar. Plus it tastes good now. So yeah, honeys, jams, salted fish, pickles. Those are all foods that are preserved by osmotic pressure.
What'd you say?
Radiation. So gamma radiation, ionizing radiation, is a great way to kill a lot of things. The radiation is enough energy to dislodge electrons from atoms. So ionizing radiation will break the phosphodiester backbone. You can actually get double-strand breaks of the DNA, and you have enough double-strand breaks, then the cell is going to die. One double-strand break and you try and go through replication can kill you. So ionizing radiation can produce the radicals, they react with the DNA. It's used as sterilization for medical supplies or pasteurizing of food. I know that at Novozymes, you use ethanol to kind of clean everything, spray it all down, and then a lot of times what you'll do is you'll put all your equipment in there that you're going to be using that should be already sterile, it's in nice closed containers, close the lid, turn on the UV, everything in that cabinet is going to get dose of radiation sterilization. Nothing's going to survive that. So then, UV radiation. So you'll do the UV so that way you can make sure you have a sterile environment. UV radiation, so this is sun damage, we all know about this. It's non-ionizing radiation, so this causes the thymine dimers. This is just as detrimental at times. It's the germicidal lamps, it's good for sterilizing surfaces, it's a little easier to control versus cesium. You would need to do ionizing, you would need cesium. So most companies that are doing non-ionizing, it's radiation, it's UV radiation. But they're both methods of causing DNA damage. And the entire point is you mess up the DNA enough, the organism cannot survive. Now, they have found weird little extremophiles that are living in nuclear reactors. So life finds a way, but the vast majority of life will not survive. Alcohols, chemicals. We use alcohol like crazy in lab. 70% alcohol, spray it on your bench, denatures the proteins, damages membranes. You can also use a mixture of an antimicrobial chemical in alcohol. So, you guys know from home, you use rubbing alcohol. If you have some kind of wound, a lot of times you'll do that to kind of clean it out. Or, just because it denatures the proteins. Usually use between 70 to 90% alcohol, aqueous solutions of them. It's an intermediate level of disinfectant, pretty good. You get most things, especially things you have to deal with on a daily basis. Obviously, it won't get everything. And it's actually more effective than soap at removing bacteria from hands, but I would not recommend using it regularly because it will dry out your hands. This is why whenever you get blood drawn or you get some kind of injection, they're going to swab your skin first with 70% alcohol. And so that's just to make sure it's clean and that they're not going to put anything into you when they stab through the skin layer. Halogens. So these do damage to enzymes by oxidizing or covalently bonding. If you mess up that 3D structure of protein, you're going to mess up its function. It's not going to be able to do what it's supposed to, effectively taking that protein out of commission. Chlorine, bromine, fluoride, iodine, these are all in that halogen category of damaging enzymes. Oxidizing agents, so again, oxidize it. Enzymes, peroxides, ozone, so hydrogen peroxide. These are more high-level disinfectants and antiseptics. They release oxygen radicals. We've talked about oxygen. It's highly reactive. It's detrimental. It's damaging. And basically you're purposefully putting, free radicals saying, here, damage stuff. I mean, you report out a little bit of hydrogen peroxide, watched it bubble. As that oxygen starts, as it starts decaying to H2O and O2. Also oxidizing agents are especially damaging to anaerobes, which makes sense, right? They don't want oxygen. Here you're going to give them a whole dose of it. And then we have aldehydes. So again, you're trying to inactivate proteins, nucleic acids, this time by cross-linking. So glutaraldehyde, formaldehyde, formulin, these are cross-linking agents. And so you can understand that that would be detrimental to cells. It's useful in science because you can actually cross-link protein to DNA, run them on gel and see what happens. But if your cell's trying to function and the DNA is stuck together or some protein is stuck to the DNA, that kind of inhibits its ability to grow. So these are considered high-level disinfectants. They're usually crossing DNA to proteins. And it's a 2% solution of like glutaraldehyde and 37% of like formaldehyde. And that's what's going to disinfect, sterilize medical or dental equipment, embalming fluid. So that's more of like the high level. We want to make sure everything is dead. Surfactants. So we use these every day. Soaps, detergents. They usually do little micelles so that way they can take things away. They have surface active chemicals. These molecules usually have both hydrophobic and hydrophilic ends, which is why they're able to interact so nicely. And so they will primarily break down, oils. And so it's like if you have oil in your hand, using soap works because they form little micelles and they carry away the lipids inside of themselves. Since they have both the hydrophilic and hydrophobic, they can wash away with water. So, soaps, detergents, they disrupt cell membranes. It's a common method to break out the cell membrane. Different chlorides. Heavy metal components, so silver nitrate. These will inactivate enzymes and other proteins. I mean, you're seriously messing with them. You're not just kind of cross-linking them or mutating them. You're adding things to them that they don't know what to do with. So arsenic, silver, mercury, copper, zinc. They're actually low-level disinfectants. They denature the proteins. For most applications, they have been superseded by less toxic alternatives. But still, you can have silver as an antimicrobial role in some surgical dressings or burn creams, catheters. So sometimes the heavy metals will do it, but they're not exactly healthy for us. So we try to use things that are a little safer. Phenols and phenolics. They're derived from phenol products. They've been chemically modified by the addition of halogens or organic functional groups such as chlorine. They're intermediate to low-level disinfectants, and so they'll denature proteins. Lysol is a great example of kind of phenol.
So would the phenols be about equal to the alcohols in the ability to kill or act as a disinfectant?
Probably.
So these
Although
are...
I would use alcohol before I use phenol. Phenol smells.
Okay, so these are in order of surfactants would be the least effective in heavy metals, then alcohol, then phenol, then halogens, then oxidizing agents, then aldehydes. That's the order of strength.
Well, aldehydes are the strongest. They're high-level disinfectants. So are oxidizing agents. So the other page was more in kind of that order. And these are kind of lower-level abilities. So I would say the alcohols, the halogens, the oxidizing agents, and aldehydes were more of an in-order thing, but
But the surfactants would be the least effective in killing microbial.
Surfactants, I don't know if they're the least, but
I'm trying to understand
they're
where you
low
have these
level.
in case it's asked on the next test.
I'm not gonna ask you what level.
Okay, well, I don't know that.
I might ask you, what is a surfactant?
Okay.
I mean, come on, that's pretty easy. It's a soap, you know, detergent. But no, the really strong stuff is the aldehydes and the oxidizing agents. That's the really high stuff. I guess that would be the take-home message of levels. So, quaternary ammonium compounds. So these are in those sulfactant areas. So we have ammonium ions, and then you can see how it gets changed and mutated. And so these are just some of the different structures. And so remember, we're talking about sulfactants, which are
Soaps.
so means you have to have some kind of hydrophilic, hydrophobic ends. So that's what these hydrophobic tails are for. So it's a great, you know, it's the way it is. That's how it's a soap, is because it has the two ends. What was it? Phenols, phenolics, just so you have an idea of what these look like. Phenol, very simple chemical structure. And then they start adding things to it, and you get these more and more complex phenolics structures. And then kind of your comparison of these chemical agents. So here is your more pretty chart. Sorry, I didn't realize I had this in it. I had to do this a while ago. This tells you your comparison of your chemical agents and your levels, where you can see things. So, soap and water. Most things, especially most things we're playing with, it's fine. But then ethanol and acetone, much better. You really want to kill everything you do or get much higher level. The iodine, the ethanol. Also, one of the things is it's not enough just to put the stuff on you like soap. And the iodine, you don't really want to just have it on there for a short period of time. That's why if you've ever gone into surgery, they put the iodine on you and they leave it because they're trying to get down a scale. They're trying to use the time. I mean, it doesn't take long, but you don't want to just, stick it on and wash it off immediately. Same thing with soap. You don't want to just kind of put your hands underwater, put some soap on and call it done. You want to give it a little bit of time to actually get through that. So, I mean, washing your hands for 2 minutes takes forever, but if you really are wanting to clean your hands, that's what you want to be doing. You want to take a little more time.
So washing your hands with soap and water kills like no bacteria.
Well,
So 2
True.
minutes kills 10%.
yeah.
So just never wash your hands.
Is that really accurate? Because I believe I saw a really recent study showing that if you wash your hands thoroughly with soap for 90 seconds, it does kill about 90% of the bacteria. Is that not accurate?
Depends on what kind of bacteria it is, right?
Yeah.
Yeah.
Depends on what kind, what is it? I mean, come on, for most of the things that you're going to deal with in your normal life, soap and water's fine. If you're coming into the medical world, soap and water might not be good enough. I mean, you don't see surgeons washing their hands for, 2 minutes. Usually
With soap and water.
they're doing the soap and water for long periods of time, getting in every single little crack to make sure you really get it, and then also using other things and gloves and probably pouring alcohol on the gloves. It's usually my method of sterilization, so I can sterilize the gloves without drying out my hands. But it's what are you trying to kill? It's one of the things you have to constantly remember.
The chemicals we're working on.
And we're covered in microbes. Microbes kind of help us. They're good for us. They digest food for us. So you don't want to kill them all. Okay, we'll cover chapter 10 on Wednesday.